So I'm going to be talking about functions of local randomness, which is sort of a topic that's already been mentioned at least a couple of times in the conference. But since it's since this is sort of online and there are people from different time zones, and so I'm going to kind of assume that everyone's been to every talk, so I'll maybe go over some stuff that some of you have already heard in the introduction, and so and in particular, okay, and so what I mean by local functions, I mean sort of we have a graph, we have some sort of randomness on each vertex, and we can think of this as just being a uniform random variable that's sort of enough to encode any sort of reasonable random process we might want. And then we want to just assign some value to this random variable and just using sort of the randomness in some local neighborhood of it. And okay, and so this is so we heard a very nice talk earlier this morning, or this morning my time at least, by Peleg, who on sort of constructing greedily maximal independent sets in graphs. And so this is sort of one sort of notion in which people have looked at local functions from sort of the combinatorics and theoretical computer science angle of sort of optimizing different properties on graphs, finding large independent sets or max cuts or that sort of thing. And there's another notion of local functions are called factors of IID, and these come more from the direction of ergodic theory. And I want to sort of, I'm mainly going to be talking about the second one, but I want to sort of link it to questions about the first one, because I think maybe this is what the audience will be more familiar with. So, okay, so just to give an example of sort of what you might want to say about local functions, you might want to find a large independent set on a random deregular graph. And so the largest independent set, as I'm sure most of you know, is about 2 log d over d density, and sort of the greedy algorithm of Lauer and Wormald we'll find an independent set of about half of this size, so about size log d over d, as Peleg described earlier today, and okay, so you can just find this sort of by greedily picking vertices, or if you do it sort of in rounds, so pick vertices with some small probability p at a time, and then sort of iteratively construct an independent set like that, then one can sort of, if you only do it for so large but fixed number of rounds, you get a local function. Okay, and but of course there's a gap of a factor of 2, and this was something that David Germanik talked about on Wednesday, and so I'll sort of just repeat sort of a really nice result of his, which was sort of answering a question of Hatami, Lovatz, and Segedi, which asked, okay, there are there local functions that get sort of close to the maximal independent sets? And the result of Germanik and Sudan is that that there are not. They showed that sort of a bit that for something that's, I think, maybe about 1.6 log d over d, above that you cannot find large independent sets with local functions. And the reason for this is sort of related to the way in which the sort of geometry of the space of large independent sets. When you're looking at independent sets that have density above log d over d, they come in clusters that are sort of well separated from each other, And this is sort of a barrier to local algorithms finding solutions and for finding big independent sets. And you can sort of argue by contradiction that you can't have a local function that works in this regime, because, well, if you did, you could apply your factor of IID and you'd find one large independent set that was in one of these clusters of independent sets. You could take a different independent set of randomness and then that would have to land in a different cluster because these clusters are not too big. Okay, so that's fine so far, but now we had two different sort of initializations of the randomness, two different sets of uniform random variables, but we could sort of interpolate between one set to another. And this would have to give us kind of an interpolation of independent sets from one cluster to the other. And it would have to bring us through a region where there's no independent sets. The argument's a little bit, is essentially this. I'm cheating a little bit, but that's more or less the argument, and so it's and so this gives you a contradiction. And then if you later on, Raman and Virag gave a more refined version of this analysis, and they proved it down to sort of 1 plus epsilon times log d over d. So log d over d is really the threshold density that you can achieve with local functions. Okay. So that's sort of the local functions view of things. An alternative sort of idea of looking at sort of local functions is what's called a factor of IID. And this is sort of very similar, except you should imagine rather than we're doing it on some finite graph like a random regular graph, we're doing it on an infinite graph. So imagine we're doing it on ZD or the infinite deregular tree. And our goal is to sort of reconstruct or construct some process sigma, which would just be an assignment of each of the vertices of the graph. And it will be a factor of IID if you just have some measurable function f that's a function of all of the randomness, and that gives you the value of the sigma at the origin. And then if you want the value of sigma at any other point, you just sort of shift your center of focus to that point, or alternatively take a shift of all of the random variables so that you move the center from x to the origin. And so you apply the same function but shifted, and that's your reconstruction of sigma. Okay. So initially this might not look like a very local function because f can depend on everything in the entire infinite graph. So that's almost the opposite of local. But it's a measurable function, and so if it's measurable, then there's approximations to it that are sort of, you can approximate the function f very well just with a function that just looks at a bounded radius. So I guess the connection between factors of an IID and local functions are that, well, any local function would be a factor of IID, and any factor of IID can be well approximated by local functions. And these come up in the sort of study of dynamical systems because being a factor of IID on ZD is equivalent to being isomorphic to a Bernoulli shift. So they're sort of related to the classification of sort of dynamical systems. Okay, so and so, you know, you can ask for various different sort of stochastic processes. Can you write this as a factor of IID? So when I was a postdoc at Microsoft in sort of 11 years ago, there were lots of questions about this. And so Holroyd and Perez and others were looking at questions of finding matchings in either of, say, point processes as factors of IID, you could, given a sort of a planar graph, you can ask, is there a coloring of the planar graph that's a sort of factor of IID? Angel et al. Showed that you could do it with 6 colors, and Team Meyer improved that to 5 colors. But I believe it's not known yet whether or not it can be done with, 4 colors, which, although you always know, of course, that there exists a 4 coloring of a planar graph, but whether or not there's a sort of one that can be realized as a factor of IID. And so when I was a postdoc, like essentially the very first question I was asked was, if you take the Ising model on the tree, when is that a factor of IID? And so, and this is something that's been bothering me for the last, I guess, 11 years. And so that's what I'm going to be talking about today. And the Ising model, as well as the Potts model and the Voter model and other ones, can be described as what Jeff Steiff called a sort of divide and color model. And this is one where the idea is you have your graph, you partition the vertices into some number of sets, and then in each set you pick a random color independently for each set, and then every vertex in the set gets that color. So the Ising model and the Voter model, for instance, correspond to divide and color models. And what Steiff wanted to know was, okay, well, first of all, I should say, suppose this division, the first step, the partition, can be realized as a factor of IID. If the components you get are all finite, then there's a natural way of, then you can also color them as a factor of IID, because essentially for each of these finite components, you could just essentially pick a leader among all the vertices by, say, taking the maximum of some independent random variable on each of the vertices in the component. And then that leader flips a coin and decides what the color for that whole component will be. And they all follow the leader. Okay. But if you end up with infinite components, you can't do this. There's no way of sort of, in general, choosing assigning sort of one fixed vertex when you have a sort of infinite number of them. So Steiff's question was, can you come up with natural examples of divide and color models that have components that are infinite that can be realized as a factor of IID? And what he suggested was a model from of an interacting particle system called the Voter model in dimension 3 and higher. And what he and he asked, can this be realized as a factor of IID? And Ling-Fu Zhang and I showed last year that it can. And so here, the random partition of the vertices of ZD into components are done by coalescing random walks. So you have a particle from starting at each vertex. They do sort of random walks, but when they run into each other, they coalesce and always follow each other after that. And these coalescing random walks will essentially partition all of the vertices in the plane into components. And so you end up with a partition of the plane into infinitely many infinite components. And then the Voter model is just to assign each component a random color. Okay, so the model that I'm going to talk about today is the Ising model. And so if you don't know the Ising model, it's a it's a model coming from statistical mechanics, sort of essentially modeling a magnetic system. But really, it's just an assignment of pluses and minuses to each of the vertex of a graph, and it's a probability distribution over that. The plus and minus of each vertex I'll call a spin, and they're weighted according to this probability distribution, which so in the weight it has this sum of sigma u sigma v over u and v that are neighbors. And essentially what it means is that the probability distribution puts more weight on configurations that have more pluses next to pluses and minuses next to minuses. Okay, so this is at least the definition of the Ising model on a finite graph. And on the tree, we can give some other very simple characterizations of it. One is as a sort of broadcast process. You start from the root and choose it, assign it to either plus or minus with probability 1/2. And then as I go from a parent to a child, I just assign a child to have the same sign as the parent with probability 1/2 plus 1/2 tangent beta, and the opposite sign with the complementary probability. And so this way, I can sort of start from the root and work down and assign all the spins on the tree. And in fact, if we did this, we could do it not just for a finite tree, but for the infinite deregular tree. And so this sort of extends the Ising model to the infinite tree. And I should say on a finite tree, this gives you the same distribution as this formula for the probability distribution of the Ising model. You can also work out what the covariances are in this. It's sort of the covariances decay exponentially, like tangent beta to the power of the distance from u to v. And so this construction of the Ising model is called the free measure. And it's not the only way of extending the definition of the Ising model to the infinite tree, but it's the one that we'll be looking at. Okay. And I can give a third characterization of, or a third construction, yes, which is in terms of what's called the FK or Fortune-Castellan model. And this is a probability distribution over percolation configurations or bond percolation configurations. So it's just an assignment of zeros and ones to each of the edges, and a 1 means we keep the edge and a 0 means we sort of throw it out. But the edges aren't independent. It's weighted according to sort of some constant parameter y to the sum of the number of edges times 2 to the number of connected components. But actually on a tree, every time you add in an extra edge, you reduce the number of connected components by 1. So in the special case of the tree, actually, this is just percolation. You're just choosing edges with some probability p. And if we choose the parameters properly, then we can make the probability of choosing an edge tangent beta, and then we'll again exactly get that. And then this will correspond to the Ising model if we do treat this as a divide and color model. So the FK model just acts as percolation. We're just picking edges with probability tangent beta. And then for each connected component, we'll either assign them to plus or to minus. So all of the vertices in the component will get the same sign. And we'll do that. And the resulting assignment of pluses and minuses to vertices will have the same distribution as the Ising model. So that's a sort of third way of building it in a sense. Okay. And so the question is to understand when this can be realized as a factor of IID. And so one thing to note is that as beta increases, there's a stronger tendency for neighboring vertices to have the same spin, and the correlations between vertices get stronger. And so we'll be interested in how different of beta affect whether or not there's a factor of IID. Okay, so and so there's two interesting thresholds for this this model. The first is called the uniqueness threshold. It's when tanh of beta is 1 over d, and it corresponds to saying that if I condition all of the vertices at level L to be plus, then that will have a sort of effect on the distribution at the root, even as L tends to infinity. So it's the question of whether or not a sort of very distant boundary condition can have an effect on the value at the root. And it only happens when tanh of beta is greater than 1, or so 1 over d. When tanh of beta is less than or equal to 1 over d, then the effect of any boundary condition tends to 0. And the reason why it's called the uniqueness threshold is essentially related to the ways in which you can extend the Ising model on a finite part of the tree to the infinite tree. And when so for larger values of beta, there's more than one ways of doing this extension. It's not unique. And so one example of this would be we assign all the vertices at level L to be plus, and then sort of look at the distribution around the root, and then let L tend, the boundary condition, tend to infinity. This will converge to another Gibbs measure or extension called the plus measure, and vertices will just be more likely to be plus. Okay. So the high temperature regime, and I didn't say it before, but beta in the physics language is the inverse temperature. So small values of beta means high temperature. So in this regime, there's very weak sort of correlations. And telling you values a long way away from the root doesn't really tell you anything about the spin at the root. So you'd think that that should be good in terms of being able to build a factor of IID, in terms of this being, the behavior being really local. And that's true. So there's there are factors of IID in this case, and in fact there's quite a number of different constructions, and maybe the simplest one is just through the FK model. You just do percolation on the edges of the tree, so keep them with probability tanh of beta, and that splits it into components that are all finite almost surely, because you were in the subcritical regime of branching processes. And that sort of independent percolation is definitely something that you can do as a factor of IID. It's it's extremely local because they're all independent. And then on each of these finite components, because they're finite, we can choose to assign them as all plus or all minus according to a factor of IID. In the way I said before, you sort of pick one vertex as a leader, and then that vertex chooses whether or not everything will be plus or minus, and the other vertices follow the leader. Okay, so there are constructions in the high temperature regime. There's another interesting threshold in the Ising model, which is called the Reconstruction Threshold. And it's this will look sort of superficially similar to the uniqueness one. We again ask, does a boundary condition on level L affect the conditional distribution at the root? But now, rather than set the values at level L to be all plus, we'll instead sample them according to the distribution of the Ising model. So we get a random boundary condition here and ask, does that random boundary condition tell us something about the root? So it's essentially equivalent to saying, if I tell you sort of these very far away vertices, does that give you a sort of non-trivial amount of information about the root vertex? And for the reconstruction threshold, the threshold is now tanh of beta equal to 1 over square root of d, whereas the uniqueness threshold was equal to 1 over d. So, so this is sort of substantially larger values of beta. Okay, so the low temperature regime would be tangent beta bigger than 1 over square root of d. And in this case, distant spins do give you information about the root. So intuitively, you would think, okay, we don't expect there to be a local sort of construction of this measure because there shouldn't be a factor of IID because, I mean, if arbitrarily far away vertices can sort of give you information about the root, how could that be done in sort of a local sense? But in general, I don't know of a proof of, just based on that one piece of information. But in the special case of the Ising model, we can indeed show that there's no factor of IID in this regime. And so in the case of the Ising model, there's actually a particularly easy way to sort of give a guess of the state of the root that does better than random chance. And that is, you just take all the vertices in level L, sum them up, and take the sign of that. And that will be equal to the same sign as the root, with probability more than a half, and sort of bounded away from a half, even as the distance L tends to infinity. So if we took that sum and normalized it appropriately so that its variance converges to a constant, that sort of normalized sum would have a sort of non-trivial correlation with the root spin. Okay, and so we'll use this in order to show that there's no factor of IID, that these sort of long range dependencies are not compatible with there being a factor of IID. Okay, and the proof is by contradiction. So you say, okay, well, suppose there is some measurable function f that realizes the low temperature Ising model as a factor of IID. Well, then we could find some other function g that also spits out a -1 or 1 that is a sort of finite, that just looks at the spins in a finite range, but is very close to f. So the probability, and so we'll call the output of g sigma prime, and we want the probability that sigma is not equal to sigma prime is less than or equal to epsilon. And just by measurability of f, there is such a function g. Okay, and so if we replace sigma with sigma prime in this covariance, we'd still get a covariance that was sort of bounded away from 0 in the limit. But now, covariances are linear, and so by translation invariance, we can sort of swap things around, so we get covariance of sigma rho with this sum of the sigma primes on level L. Okay, so how does this help? Well, the sigma primes have very short range dependence. So they're based on sort of just the random variables within distance r. And so if you take u and v that are distance more than 2r apart, sigma prime of u and sigma prime of v will be independent of each other, and so have covariance 0. So when we work out the covariance of the sum of the sigma primes, basically most of the covariance terms are 0. And so the variance of this term goes to 0 in this regime. And because they have a finite range of correlation. And so this means that this covariance must tend to 0, and so it gives a contradiction to there being a factor of IID. Okay. So there's a factor of IID when it's high temperature. There's no factor of IID when it's low temperature. That sort of raises the sort of natural question of that Lyons posed of what happens in the intermediate regime when beta is between 1 over d and 1 over square root of d. Is there a factor of IID? And yes, as I was saying, this is a problem that, you know, I was like the very first question I was asked at the beginning of my postdoc, and I've been thinking about it for since then. So before I tell you our results, I want to sort of tell you a sort of series of failed attempts which sort of lead towards the final result that we have. So the first thing you could try is just what we did in the high temperature regime, where we used the FK model. But in this case, it's supercritical percolation. The component, or at least some of the components, will be infinite, and there'll be no translation invariant way to assign the colors. So that won't work. A suggestion of Perez was to construct it based on the Glauber dynamics Markov chain for sampling from sigma, and this is something that works in the high temperature regime as well. So the Glauber dynamics is a sort of Markov chain that you can use to sample from spin systems like the Ising model, or really any distribution. You sort of give each vertex a rate 1 Poisson clock, and then when the clock rings, you update it according to its value given the stationary distribution. So you can define this on the sort of infinite tree. And you could use the coupling from the past approach of Prop and Wilson, where you sort of say, okay, we'll start this at time minus infinity, run updates up to time 0, and hopefully the sort of initial condition at time minus infinity didn't matter. And you'll get an exact sample from the distribution. So this works in the high temperature regime, but in the intermediate temperature regime, you get different initial conditions if you started from, say, all plus versus all minus. Perez had a suggestion of maybe trying to start with an IID initial configuration, but simulation suggests that suggestion doesn't converge almost surely, and so doesn't lead to a factor of IID. Okay, so attempt number 3 will be just to sort of assign the vertices in some random order. So this is something you could do on a finite graph. Just pick an order, assign, you know, the first vertex is equally likely to be plus or minus, assign the second vertex given conditional on what you did for the first vertex, and so on. But on an infinite graph, there's no sort of translation invariant ordering of all the vertices. But what you could do instead is give each of them a time between 0 and 1. This is sort of similar to what Peleg talked about earlier this morning. And also a random variable uv, which we'll use to decide whether it's plus or minus. And so you could say, okay, we'll set sigma v equals 1 if uv is less than or equal to the conditional probability that sigma v equals 1, given the ones you've set before, or so that's the sigmas of the u that have times that happen before tv. Okay, so this is a valid construction for a finite graph, and you can ask, you know, can we extend this to an infinite graph? Well, one problem is there's actually multiple solutions to this set of, this is really a set of equations, and there's more than one solution to it. You can have a solution that's effectively the plus measure or the minus measure. And it's still a sort of open problem as, can you find, in a strong sense, a solution that corresponds to the free measure. And the sort of difficulty is sometimes your random variable u will be very close to sort of the boundary here. So you just have to shift u or shift the probability a little bit, and you'd switch the sign of sigma v from plus to minus. So and it could be that sort of that's affected by some very, very distant faraway vertices. And it's sort of hard to control the effect of those faraway vertices when you're sort of really on the knife edge between 1 and -1. So maybe a softer approach to setting the values of vertices would be, rather than sort of exactly reveal the value of a vertex, I'm going to reveal sort of noisy information about it. So each vertex will have a series of times TVI given by a Poisson process. And at each of those times, I'll reveal HVI, which will be either plus or -1. And so the probability that H agrees with sigma will be something more than a half. So let's say a half plus alpha. And okay, suppose we could construct something like this as a factor of IID, then we could sort of extract out sigma, because if I let xv be the sum of the first n of them, then, well, basically this is xv will be a biased random walk, and if I let sort of n tend to infinity, if xv tends to plus infinity, then sigma was 1. If it tends to minus infinity, sigma would be -1. But I still can't construct this, again, because I can't really control the effect of what's happening from very different vertices. There's still, in a sense, hard choices being made. But the motivation of this final attempt would be sort of to look at what happens when alpha is very small, and you're just getting a very small amount of information at each time step. Then if you rescaled, x of v would look like a Brownian motion with drift. Positive drift if sigma was positive, negative drift if sigma is negative, and this is going to be the construction we use. So what we're going to do is build a factor of IID of a more complicated process. It will be the process xv of t, which will be a stochastic process, which is sigma v times t plus a Brownian motion. And the Brownian motions will be independent for different vertices in the graph. So we're building a Brownian motion with drift, and the drift is either positive or negative, depending on the sign of sigma. Okay, so that's, and if we could construct this, then by taking the limit of xv, that would tell us what sigma should be. So this is the object that we want to construct as a factor of IID. And now, of course, it would be very easy to build if we already knew the sigmas, but we don't. That was the whole point of this construction. So how can we make such a set of x's without first choosing all the sigmas? Well, let's try it just for a single vertex, pretending the graph was just a single vertex. Then we want to make, so we want to construct it, but without sort of first making a choice of what sigma is. And I'll let ft be the filtration generated by xt. And then, okay, so to calculate the probability, so if we just ran it for time t, we'd have a Brownian motion either with a positive drift or a negative drift, but we wouldn't be able to tell at time t exactly whether the drift was positive or negative. Those distributions are mutually absolutely continuous. But you could work out what's the probability that sigma is plus given what you've observed up to time t. And actually so the expected value of sigma v up to, given what we've observed up to time t, is you do Bayes rule essentially, and you get that it's tanh of xv of t. That's just a calculation. And so it turns out if we want to build xv of t, one way of doing it is to write it as a stochastic differential equation. So where dx is tanh of x dt plus dbt. And in distribution, this will give us a process with the right distribution. Okay, so okay, so but that's just I should say, and this is a very sort of simple case where it's just a sort of one-dimensional stochastic differential equation. The sort of the coefficients in the SDE are well behaved, so there's a unique strong solution. Here, a strong solution means x is really a function of b, which is what we want if it's going to be a factor of IID. But of course, we want to do this for all of the vertices in the graph simultaneously. And okay, to do this, we want to I want to introduce the Ising model with an external field, and this just means sort of an extra term, sort of sum of HV sigma V, where H is basically just biasing the sigmas to either be more likely to be positive or more likely to be negative. And then if we then another Bayes rule calculation will say that the expected value of sigma V, given everything we know up to time t, will just be like the expected value of sigma V in the model where we have an external field given by the process x at time t. That's just a calculation you can do. Okay, and the system of SDEs that we want to solve is dx is equal to this conditional expectation of sigma v dt plus db vt, where these are independent Brownian motions. Okay, but this is now an infinite dimensional SDE. Those are sort of much harder to check if there exist solutions to, and our system of SDEs doesn't seem to fit in any of the sort of standard examples where there's sort of existence and uniqueness. And in fact, this particular SDE does not have unique solutions. There are multiple strong solutions, including ones that sort of correspond to the plus measure and the minus measure when we're in the infinite, in the intermediate regime. Okay, so we need not only do we need a solution, we need one that we can check corresponds to the free measure. And so the way we can do that is by just applying this, by just constructing these SDEs first on a finite graph. So we take the root, take a ball of radius rho, and then do this construction just on that finite graph, and we'll call this XR. And then hope that as R tends to infinity, they converge, and indeed that's what happens. So our main theorem is that for not quite all of the intermediate regime, we prove it for tanh of beta between 1 over d and a constant over square root of d, that these converge almost surely, and that the limit that you get is a factor of IID. Okay, so we have to check a couple of things. First of all, that the sort of, as we let the radius grow, that these processes do indeed converge almost surely. And also, when we're applying this to different vertices, the balls will have different centers. And so we need to check that we get consistent results when we take different centers. But that turns out to be almost exactly the same sort of thing to check as the effect of letting R grow. So I'll just mention that first discuss that first issue. And so what we want to do is compare XRV with XR plus 1V, which is really, so comparing what happens in a tree of depth R to a tree of depth R plus 1. And the way we do this is essentially to interpolate between the two. So in a tree of depth R plus 1, for the edges in the bottom row, rather than having a term beta sigma u sigma v in the probability formula, we'll have a term gamma times sigma u sigma v, and interpolate from gamma between 0 and beta, which will in effect interpolate between XR and XR plus 1. And then we differentiate, and so we sort of differentiate the solution of the SDE, and we get this rather involved integral of sum of products of covariances. And these covariances are covariances with a random external field. And what we need to do is show that this derivative is sort of, small when R is big, that the effect of sort of changing the interaction on these faraway edges isn't really affecting what's happening at the root. And there's sort of the difficulties in doing that are, well, most of these covariances just involve two different sigmas, so they're all positive, but they're random variables because the external field is random. And then this last term is a covariance with one sigma and then covariance of that with a product of sigmas. This final covariance can be both positive or negative. And we sort of can't afford to just take the absolute value of that. We need to take advantage of a lot of cancellation that's going on. And well, so there's a lot of, so it's quite a delicate analysis to look at this, but looking at the time, I am not going to say how we do that. And you should probably be grateful for that because it's kind of messy. But we sort of have formulas for these covariances and sort of do some inductive coupling to get sort of certain decay of correlation properties that we need. Okay, but I'd sort of like to finish off in the, I think, 1 minute that I have left to mention just some open problems, which is really the main reason for giving this talk. So, okay, the most basic open question is to just extend this analysis to the full intermediate regime. I think our factor of IID should work for all the way up to the reconstruction threshold, 1 over root D. And I think maybe if we worked harder, at least for large values of D, we might be able to prove that as well. But, we had to pull out stochastic calculus in order to sort of, whereas, it's for what is a very discrete model. And so it would be really nice if there was a simpler factor of IID, and I'd be very interested if, and I hope maybe someone here might be able to find such a process. A more sort of fundamental question is to sort of better understand the relationship between factors of IID and this reconstruction threshold. So so it seems like, up to this sort of constant factor that we're missing, we've established this relationship in the case of the Ising model, but it seems like it should occur in other models like coloring or the hardcore model. And for example, in the case of the hardcore model, this is to sort of link back to what I started talking about. So the hardcore model is sort of a probability distribution over independent sets. And so you can ask when it has a factor of IID. And so there's a parameter, the fugacity, for that. And sort of and what corresponds to the reconstruction threshold in the hardcore model is exactly when you get independent sets of density log d over d, which was what Germanic and Sudan and Raman and Virag sort of established was sort of the critical threshold for local functions for finding large independent sets. So that sort of suggests that this correspondence between factors of IID and reconstruction and extremality should be a broader one. And finally, the last question sort of related to a question that Jane Gao asked in Peleg's talk this morning and it's sort of, if you have a factor of IID, does that tell you something about a lower bound on the partition function of a sort of corresponding random graph? And I think this is something that could be useful in a number of applications, but I think maybe I should stop here and ask if there are any questions.
Thank you very much. Any questions?
I have one, if I may.
Sure.
So you gave this example of the SDE in the case of one point with the hyperbolic tangent.
Yes.
And so when you are on the tree, this SDE with multiple points. So there is this expectation, the slide just after, I think. Yes, there is this expectation with respect to XR of T of sigma V to kind of run the SDE. How explicit is this expectation? Do you need it to be
I think very explicit. So I mean, what this is sort of encoding is it says you take the Ising model on this tree of depth R, and then you use an external field where the external field at vertex V, or let's say vertex U, is XUR of T, and then calculate the expected value of the spin at vertex V according to that Ising model with external field. And so in a finite graph, that at least that's a sort of, nice smooth function of X.
Yeah, okay, I guess explicit, I can see it, but if you were to do it in practice, say, would you be able to run that SD without computing the sum of all the hypercube that you're using for the underlying?
Yes, I mean, so in terms of whether or not can be done well computationally, well, these graphs are trees. So if you know the external, if you have a tree with sort of a given external field, then you can calculate the marginals using sort of belief propagation messages on the tree, say. And so that could be done in, I guess, linear time in the size of the graph.
Okay. I see. So with this belief propagation, you could actually run this SD rather efficiently.
Yeah, well, I mean, okay, so of course the ball of radius R grows exponentially in R. And our error bound, I guess, is also exponential in R. So I guess we're only getting a sort of polynomial trade-off in the running time. So I'm not sure, not like super efficient, but maybe not too bad.
Okay, thanks. It clarifies. Thanks a lot.
Okay.
Any other
Great
questions?
talk, by the way.
Oh, well, thanks. Yeah, I wouldn't suggest that this is.
Hi, Professor Sly.
Go ahead.
No,
Oh.
I don't know what happened with yeah, just great talk. Thanks.
We have one more question, I think.
Yeah, I have a question. So in all the different models, there are some physics meanings about some parameters and structures. But for our students in graph theory, usually we don't have the background of physics. So it's I think there's some subtle points. It's easy to make a mistake. Yeah, what's your suggestion to make the connections of graph theory model to the
Okay, so in a sense, there's not, you know, the Ising model on the tree at least can be, you know, we have sort of descriptions of it in terms of sort of. Oh, okay, so I have to more slides than I. Yeah, there are sort of some sort of fairly combinatorial descriptions of it. So in terms of like a broadcasting process, and then it's really like as you go along each ray in the tree, it's really a two-state Markov chain, which is I guess, you know, or in the FK model, it corresponds to doing independent percolation on the edges and then coloring the components at random. And in a sense, we're not really using much more than that. There's a lot more physics in I think this understanding of large independent sets, whereas for the factors of IID on for the Ising model on the tree, really, in a sense, most of the attempts have just been kind of bare hands attempts to sort of understand this sort of fairly, at least simple to describe distribution. Yeah, but I'm not sure that how well that answers your question, but it's yeah.
yeah. So to be specifically, I mean, yeah. Thank you for this explanation. I mean, especially when we use the Markov chain, you know, there are many different variations. We may want to design new rules or new models, but a lot of time we may miss the whole picture about the physics meaning and lost the connection, and then we get some things very strange.
Yeah. Yeah. So I think in general, some of the sort of problems I mentioned at the end might be useful to understand some of the physics predictions, particularly like so in terms of these large independent sets, for instance, there's sort of heuristics coming from physics saying that, you know, this sort of reconstruction property, being able to estimate the spin at the root given far away vertices, is really closely linked to the solutions having some clustered form.
Should I tell them to stop?
No. And yeah, well, I'm not sure I have a very good answer to that. But there's but in the case of the Ising model, I think there's sort of a simple enough description, and the behavior is simple enough that it should be possible to tackle it without really any additional knowledge of the processes. Okay, so I think we're probably running over time, so I should stop.
Fine. Thank you.
Okay.
You can complete the private chat if needed. Thank you very much for the very nice talk.